Hey everyone, and welcome to another Into the Terminal. Today we're going to be talking about troubleshooting networking. So, in all of our troubleshooting episodes, we start with a slightly different format where we first talk about the tools we're going to use to perform our troubleshooting. So, let's jump into the terminal and we'll take a look at what we're going to be using today to help us out. So, few applications are quite as ubiquitous as our friend Ping. That's going to be one of the key ones for troubleshooting network issues today. So just to refresh your memory, so Ping takes a host name or IP address as an argument, and will send ICMP packets to that host, and then that host responds with a echo packet back. So what we're being told there in the output is the size of the packet that was sent, where it was sent, and the response that we got back. We're given the sequence so that if, for example, we are having intermittent network issues where they're dropping packets somewhere in the network, we would see the sequence be skipped to tell us that we're missing pieces. Uh, Time to live is how many hops it can do. And then the time is the round trip time between this computer and the target computer and back again. So basically, the latency. How long is it taking for this ICMP echo to be received, and or sorry, ICMP packet to be received and the echo sent back to us? So pretty quick, right? 8.4 milliseconds, 16 milliseconds. That's quite good. I have been in places where it's been like 500 milliseconds, which is not great, and indicates there's a lot of latency on your line. All right, another tool, tracepath. All right, so tracepath sends a series of UDP datagram packets. And the way it works is it sets the time to live on the packet to be incrementally larger every time it sends out a packet. So it actually sends out a huge series of them. And what happens is when the recipient receives the datagram packet and it sees that it has exceeded its time to live, it sends back an error response, which is how we identify who that person was that received our packet. So we could see out of here, let me get Control C here. So we could see that it was received by my local system. Then it went to our default gateway, and then it went to a machine called Security Gateway, and then it went to my internet router, and then it went to somewhere in my internet service provider's network, and then it bounced around to a couple of IP addresses, and it still continued to bounce around. Now you'll notice that there's a bunch that say no reply. So network devices can be configured such that when they receive an expired packet, they don't send that error response back. And so tracepath will send 3 packets to a recipient. And if it doesn't get any response to those 3 packets, that's what you get with the no reply. And then it tries to go to the next hop. So it is possible that the no replies are they've just turned off error messaging, so we don't get a response back. Or it could be that like something's happened and we're not getting responses past this location. By default, tracepath will send out 30 hops of data. So if between yourself and the recipient getting those packets is more than 30 hops, you may need to use a command line argument to make it so that your packets are there's more series of packets sent out than the default, which is 30. There is another application called traceroute, which is a little bit older application. So tracepath is kind of the new one, but we can also use traceroute. And traceroute kind of does the same thing, where it sends out a series of ICMP packets by default. So this is the same type of packet that a ping sends. Same idea. I'm going to send out with a time to live so that at some point someone's going to receive an expired one and it's going to send back an error message that helps me identify who that person was. Um, the other thing with trace route is you can use the capital T option to, instead of sending out ICMP packets, you will send out TCP formatted packets. So remember I said that systems can be configured to not send back data when they receive error stuff. Well, that's true for different protocols as well. So someone can choose to configure their machine to not respond to ICMP packets, but would respond to TCP packets. You can also do with both tracepath and traceroute port connections, so that you're not just checking to see whether you can get a packet to this host, but you can actually check to see whether you're getting a packet to the host to a specific port number and service on that host. All right, our next application for our network troubleshooting, dig. So dig is a DNS lookup tool. There are several others as well, like host or NS lookup, that are more traditional. I like using dig because dig actually gives me the full DNS record that goes with the DNS lookup. So for example, if I just did a host google.com, right, it comes back with the name and the IP addresses. Whereas if we look at the dig output, it gives me the time to live information. So these records will live in any cached DNS server for 53 seconds. It also gives me the type of record. So an A record tells me this is name to address association, but there are other types of DNS records too. We could come across a CNAME record, which is like a DNS name alias. And dig would tell us that it's a CNAME record, whereas the other tools don't necessarily give us that context. The other thing that I like with dig, and NSLOOKUP also does this, is it tells me the server that it asked the question to. So down here in the tail, it tells me where my request for DNS lookup went. So I know that the data passed back through that server. And that might be important for doing things like um, troubleshooting DNS server settings, or something along those lines. So I like Dig as my DNS troubleshooting tool. All right, then we start to look at some other more local system settings tools. So for example, we have IP. IP is the, like, everything you ever wanted to know about your networking utility. So there are several subcommands with IP that give you specific things. So for example, IPA shows you your configured IP addresses. So we have the loopback interface, this is 127.0.0.1. We have an IPv6 loopback interfaces as well. My network interface ENP0S3 has two IPv4 addresses assigned to it, as well as an IPv6 address assigned to it. We also have IPR. IPR shows you the routing configuration of this machine. So we can see that the default route on this machine is configured to send packets to the IP address 10.0.2.2. And then also we have our two IP addresses assigned to this machine. So for 10.0.2.0 network, we're directly connected, meaning we don't have to use the direct our default route. And then we're also directly connected to a network called 192.168.10 dot. That also would be direct transmission rather than sending data through the default route. Um, for me, this is a little bit more difficult to read. I like the tabular output of route. So this is the same information as IPR, or a lot of the same information as IPR. The big difference is that it is more tabularly formatted with route output, as opposed to IP. The other thing I did was I threw in the -n option, which says, show me only numbers. If I don't use -n, it would try to do DNS lookups for any things like the default gateway's IP address. So a lot of the option, or a lot of the commands that we use have behavior that it does one thing, and we'll actually talk about this in the whiteboard section, one thing for IP address arguments, and something slightly different, a slightly different path for if it's handed a host name argument. All right. The last command that I'm going to show you is also a very large one. So that is nmcli. Now, nmcli is the network manager command line interface. Network manager is how networking is managed on Red Hat um, distributions. So that would be RHEL, which is what I'm using, CentOS Stream, as well as Fedora. They all use Network Manager as the application that controls their network settings and at boot time takes care of configuring the network interfaces that are attached to the machine, a variety of other things. So NMCLI also has um, availability or a hook into bash completion. So what I did was I typed nmcli, hit tab and tab again, and it says, here's the next argument that you can pass to nmcli, one of these things. So I could do an nmcli connection tab. And if I hit tab one more time, it'll say, okay, if you're going to do nmcli connection, here's the third argument on the command line that you can use. So I could do something like show, and it'll show me the connections that are active on the machine. I can also do something like nmcli connection um, show uh, tab, and these are the things I can offer. So maybe EMP0S3, and it goes into that specific connection and then shows me all the parameters that are affiliated with that connection. For example, I can search in here for IPv4, and these are the IPv4 settings that are applied to this network connection. And so we can see things like the IPv4 addresses. So I have a statically configured IP address 192.168.10.222. And then it turns out my other one is assigned via DHCP. There's also a variety of settings for IPv6. And if I keep scrolling down, this is probably the one of the nice things. I said my other address was configured via DHCP. So towards the bottom of the NMCLI show connection and the name, or sorry, NMCLI connection show and the name, it'll actually show me the DHCP lease information that was received for any DHCP configured addresses. So 10.0.2.15, that was the IP address that my DHCP connection was assigned. Um, 10.0.2.2 was the default gateway IP that came with that lease. 192.168.1.1, that was the DNS server configuration that was provided as part of that lease. And so you can see all of the different DHCP lease parameters that were provided with those interfaces that were configured via DHCP using NMCLI, connection, show, and then the connection name that you want to display, right? So this NMCLI connection show and then the name gives you all that detailed information. You would also use NMCLI to change any of these parameters. So when I added that secondary IP address of 192.168.10.222, I used NMCLI to apply that change. And it gets stored in a backend database that NMCLI stores network settings in so that when I reboot the machine, changes that I make using NMCLI will persist between reboots on the machine. All right. So those are the tools that we're going to use today: ping, tracepath, dig, IP, maybe route, and NMCLI. So don't forget to bang that like and subscribe. After we transition to the deeper dive, we'll take a look at some how do packets actually flow through networking. And then we'll troubleshoot a couple of situations where things aren't flowing correctly. And we'll use that understanding of what it's supposed to look like to figure out where we need to focus our efforts for troubleshooting. So stay with us as we go into a deeper dive in just a moment. All right. So we're going to take a deeper look into networking. And we're going to start by doing some concept stuff on the whiteboard of figuring out like what is it supposed to look like when I'm doing network operations through a machine. Also, I'd like to remind you that this is the time where if you have questions and you're watching live, you can put them in the chat. If you are a deferred viewer, please feel free to leave us a comment. Myself, Nate, producer Eric, we all pay attention to the comments and will likely respond to questions placed there. All right, so let's jump onto the whiteboard here, um, and let me kind of put together some really terrible artwork that you all can make fun of me for. All right, so there's my computer, right? And a really terrible rendition of a computer. But there is a network address which is 10 dot. I've forgotten what it was. Let me take a quick look at IP. 10 dot 0 dot 2 dot 15. That's what we saw during the critical path when I ran IPA. It showed me my configured IP addresses. We also saw it in the nmcli output. And so that's how my computer is connected to the network. And there may be other computers connected to this network that I can directly talk to on my subnet. But there's also a default gateway connected to this network. And its IP address is what we saw in the route command and IPR commands, which is 10.0.2.2. Oops. All right. So when my computer wants to send something to send to a computer that's outside of this network, the 10.0.2 network, it has to route that traffic to the default gateway. And the default gateway has another IP address or another interface that goes somewhere else, which may be more of my corporate network or internet service provider's network. It may be direct out to the internet, depending on your configuration of your network and how you manage it. All right, but then on the other side of that fluffy cloud of the internet, there's another computer, or maybe another computer. So these were two that we used during the critical path. Both of these are configured to respond to ICMP echoes, right? To pings that are sent to them. Um, and when we were looking at the tracepath output or the trace route output, what we were really looking at was what was happening in the network and internet fluffy cloud. So we were seeing our packet left our machine, hit our default gateway, then went through our local network infrastructure to our internet service provider, then out to other routers on the network or the internet rather, and then eventually would land on whatever this target host was, and then packets would come back to us. So trace route and trace path are really helpful for kind of seeing what are all the stops that your packets take on their way to get somewhere. Now, there's also one other thing that is out here. Your DNS server is also out here somewhere. So on my machine, it has the IP address 192.168.1.1. So that's a non-routable IP. I know it has to reside within my local network somewhere. Um, but we could use a internet connected um, DNS server as well. And so what happens is when I use a command like ping, and I give it a host name, or I use tracepath and I give it a host name. Well, the first thing we need to do is figure out what the IP address on the internet is, or the local network is of that host name. And so before it does anything, it'll actually kick off a DNS request. Behind the scenes, to then figure out what IP address goes with this host name. And there's a variety of things that happen there. The first thing we do in the DNS lookup is we actually look at a flat file, and this is how most machines are configured. So we'll look to see if there's a DNS entry in Etsy hosts, which is a flat configuration file that resides on your local machine where you can tie specific IPs to specific host names. If it's not in there, then it'll check some other network services that most people don't use anymore. And if it's not in one of those, because most people don't use them anymore, it'll then do a DNS inquiry to figure out what IP address goes with this host name. And with the DNS server inquiry, it actually looks at a file called etsyresolve.conf. And that's where our DNS server specifications are for this machine. So we'll take a look at this file a little bit later in the episode. But basically, it says these are the machines you should query for DNS lookups. And on my machine, the only one that's listed in there is that DNS server on my little terrible diagram, which is 192.168.1.1. So once we get the IP address that goes with that thing, then ping will actually go to whatever the IP address is that it looked up. Let me do a quick look here. All right, so maybe it's 140, whoops, 142.250.105.104. And that's where it'll actually send the traffic, right? Who it looked up with DNS. But because you provided a host name as your argument, then when it provides you the receipt of those packets, it'll actually resubstitute the host name as in its output. So you ping www.google.com, you'll get back a response that www.google.com responded to you and some metrics on round trip time and other stuff. So DNS is pretty seamlessly integrated in all of our things. And it happens behind the scenes, and most people don't pay attention to it, which is great until it doesn't function properly. So when we do this ping, it does a DNS lookup first, figures out the IP address that needs to go with it, then takes that traffic. It will assign it to the network packet that needs to be sent. Because it's not for our locally connected network, it then goes to our default gateway. Our default gateway will then route it to the internet. And then the internet routers will bounce it around until it goes to Google, who then responds back, which then gets delivered to our default gateway, which then makes its way back to us, right? So that's the flow of things. If we use a host name, we will first use our network uh, settings. It will be like from here to here, out here to our DNS server and back again to do our DNS lookup. And then it will go from our computer to our default gateway, bounce around out here on the internet to our target host, and then traverse back again. That's the way normal networking things happen. All right. So let's let's turn off the whiteboard, and then we're going to go back to our computer and we'll see what happens when things go awry. And producer Eric, if you could turn that off for just one moment so I can break it, and then we can troubleshoot what happens. All right, so we can pull back up, um, and now this machine is not functioning properly. And we can see that because when I do things like ping, it's it's not giving me that like 64 byte packet round trip time, et cetera, that we were getting before. And this actually is affecting all my tools, right? If I do a trace path, nothing. Um, but notice that for each of those tools, I was passing a host name as the argument. So when I'm troubleshooting a network problem, um, I want to try and keep things as simple as possible. And we know that if we use a host name as an argument, we actually add a complication into how we're passing network traffic around in the network. That complication is we need to first do a DNS lookup on the host name before we can do anything else. So what we're going to do to decide whether that complication is causing our problem or not is we're going to run the same two tools but remove a host name and replace it with with an IP address. So ping by IP address is working just fine. Tracepath with an IP address is kind of working. Oh, maybe we need dash n. There we go. Um, the reason it kind of stopped was because it was trying to do a DNS lookup on all the machines that we connected to then show me the host name in the trace path output. So -n says, give me just the numbers. Don't worry about DNS lookups. So now I'm seeing the IP addresses of all of the machines that I'm connecting to send this packet on its way to 4.2.2. So my symptoms are using host names doesn't work. When host names are trying to be resolved, like I do something like dig, not working. But when I use IP addresses, that seems to be functioning fine. These are the hallmarks of a DNS problem. And there's a famous internet haiku about DNS of it can't be DNS. It's not, or no, sorry, it's not DNS. It can't be DNS. It was DNS. Um, so because DNS is kind of ubiquitous and involved in all of these things, like we saw tracepath just kind of froze, even though I had passed an IP address because it was trying to do DNS lookups on those return IP addresses to figure out and display more human-friendly output. So it'll manifest itself in weird ways. But the way that we troubleshoot it is we use tools like ping, or we use arguments like -n that turns off DNS lookups for tools so that we can see whether it's an IP layer thing, a networking layer thing, or a DNS thing. All right, so I told you earlier that etsyresolve.conf is the place where my DNS servers are listed. And so here's my DNS server. One of the things I can do is I could use a different one. So I could put in here name server and somebody else's name server. 4.2.2 is a internet provided name server. And now we can do things like ping www.google.com and things are working again, kind of. Um, so that tells me again that this is reinforcing that I have a DNS server problem. I don't like to use someone else's DNS. Like the whole reason that we have DNS internally is so that we can have our own internal the network namespaces that we use for machines and a variety of other things. So if we don't use our internal DNS at all and we use someone else's DNS, um, that's probably not going to be good long term. So let's figure out what's going on with our DNS server. All right, so let me delete the other one. So we're now just using that one that was in there. Um, so we could do things like ping it. And it's not responding to pings. So it looks like the reason that we're having DNS problems with the server is because it's not attached to the network, or my network routing doesn't get me to it, um, which would explain why it's not functioning properly. But there's something else. So one is I can try and figure out if that is another server, what may be wrong with it. But often what I find is it's actually not the server on the other side of our DNS queries that's the problem. Often it's our own local configuration that's the problem. And that's what's happening here. So if we take a look at the nmcli connection data for our internet, for our IPv4 address, right? So this is what we saw before we transitioned. We're going to look at the connection details for ENP0S3. And I said at the very bottom, you get a list of all the DHCP provided data. And what I want to draw your attention to is that line right there. So when I got a DHCP lease, it said, here is your DNS server. And that gets populated into our etcresolve.conf file. But if I look at my resolve.conf file, that's not the IP address that's in there. And you may have noticed that there's a comment in this resolve.conf file which says, this file is generated by Network Manager, which means don't manually change it. And somehow the network or the name server entity was changed to not match what was provided by our DHCP lease. So I'm going to go in and manually change it back. So now it matches the DNS server that was provided to me as part of my DHCP lease on this interface. And now if I do a dig, which we know is a DNS lookup tool, it's working. And if I ping, it's working. So the problem was that our DNS server was misconfigured. The local connection to whatever DNS service provider is out there that we're supposed to use was incorrect. And because we were routing packets to another machine that wasn't a DNS server, we weren't able to perform any of those DNS lookup activities. All right, so how does this happen? One is just like what we saw here. Somebody goes into the file and changes it. Very common. Um, and they put the wrong data in it. In my experience, that's been one of the most common reasons why this particular problem happens. Something else that could happen is maybe we have multiple interfaces, and the DNS provider for another interface gets put in on top of our preferred one. So another common resolve.conf problem that I'll see is we'll see something like this. Where you may have more than one name server specified, but the wrong one is listed higher in the file. And what will happen is it will cause DNS lookups to be very slow, right? So notice that it worked eventually, um, and now it's kind of working, but super slow. And that's because having the wrong DNS server in our file higher up, they're queried in order. And so we're trying to hit that one that doesn't exist. We have to wait for it to time out. And then it goes to the second one on the list, which does exist and provides the right response. And then when we get our ping response back from that machine, we have to resubstitute its IP address for a host name. So we again do a DNS query, which we have to wait for that top server to time out before we can get to the active DNS server, right? So DNS server settings is one of the more common causes of network problems, and you can troubleshoot it by one, using IP addresses as part of your tool set of using your tools to verify connectivity at the IP level. And if you have success there, but not success with host names, then that will direct your search to like, what is the correct DNS server I should be using on this machine? Are those settings reflected in the configuration files like etsyresult.conf that I'm supposed to be using? Or is this incorrectly referenced in my maybe something like my network manager configuration for this interface? So you can start to look at what your settings are and where they should be applied. All right, so let's take a moment and look at the chat here. Um, I don't really see any questions on the chat. Um, I see TTY Bitnik says, indeed, I had this problem in some container images. It's always worth checking. So yeah, like containers have their own um, network settings, which means that they have their own resolver and they may send packets in a different way than the host operating system. All right, so let's flip to the whiteboard and we could see what was going on with that problem. All right, so this is where we left off on the whiteboard. I said that when we were using host names like www.google.com, we had to do this top yellow path of doing a DNS lookup to figure out what that IP address is. So we can put the IP address in our network packets to get them to the destination. But the problem was that when we were looking at that yellow path, it was following this first hop and it was going out to the network, but instead it was being routed to this incorrect host name that didn't exist, that didn't provide DNS services. And so that connection would time out. And then we would just kind of see emptiness when we were using DNS queries. When we put it in so that the incorrect server was listed first, we'd wait for that timeout to occur, and then we'd do the DNS query against our actual DNS server that was also listed as a secondary in our etsyresult.conf. So we got the resolutions, they just happened really slowly because we had to wait for that first server to time out for every single DNS query our machine did. All right. So uh, I'll have to draw again. So let me break my machine in another way, and we'll take a look at another network problem. 1 second. Pretty sure, yeah, here we go. Because I want to break it in a way that not everyone sees immediately because they watched me break it. All right. All right. Okay. So let's bring up the host because now it's broken and not working the way we want. So, user calls you up, says the internet's down, and you're like, well, I don't think that's true. Let's look at the machine itself and make that determination. So let's try our same troubleshooting, right? Ping and a host that should be up and responsive. Nope, not working very well. Okay, but we know that that could, because we're using a host name, it could be a DNS problem. So let's also ping by IP address. No responses, right? Destination host unreachable. Woof, that's rough. So this looks like a real problem. So let me see what else we have going on here. Um, so first, we're going to see if our IP addresses are configured. All right, so we have two IP addresses on ENP0S3, 192.168.10.222, and 10.0.2.15. And so if I connect to it, I should try to connect to another machine on my local area segment. That would be my next guess. So like ping 10.0.2.2. That's on my local area segment. And that's working. Cool. So my interface, my network interface is able to pass packets to another machine on my network. But let's try our DNS server. Destination host unreachable. All right, so we're looking at traffic is able to pass to my local machines that are connected to my local area segment, but they're not able to be sent to machines outside my local area segment. Hmm. Hmm. So you recall when we first started talking about the correct flow of traffic to different machines on the network, that if I'm sending something to my local area segment, it's just put on the interface and sent. But if I'm trying to send something to outside of my local area segment, it goes to a specially designated machine called the gateway. And the gateway is then connected to other networks and up into the internet to route the traffic to wherever that end host is going to be. So my problem is manifesting as local area segment works fine. Anything on the other side of that gateway, not fine. So that would lead me to start looking at gateway things. So you saw me ping one of the machines, 10.0.2.2. That's fine. But if I try to ping outside again, we're getting this host unreachable error message. But I want to call your attention to something. Notice who this error message is from. So in our earlier things where we were passing traffic back and forth or watching things like tracepath, all the traffic was being routed to a gateway called 10.0.2.2. But now when I'm doing things outside my network, I'm getting error messages from a different host name or a different IP address, 192.168.10.222, which is one of my configured IPs, but that's not the one that was routing traffic out to the network earlier. So we know a couple of other commands, another couple tools that we have in our toolbox. We could do something like an IPR, or I said the one I like more is route-n. And this is what my machine's routing table looks like. So right there, if traffic is destined for the 10.0.2 network, that is a directly attached network to this machine. No gateway is required, right? 0.0.0.0.0, no gateway is required. If I am sending traffic to 192.168.10 dot network, no gateway is required. But those are my only two directly connected networks. So anything outside of those, if I send traffic, it's going to have to go to my default gateway. And here's where the weirdness happens. I have two default gateways. So this 000 for the destination means all destinations. And then the gateway is the IP address of the router that should receive that traffic to pass it off to the next side of the network or internet. And I have two of them. So if I have two of them, which one gets used? It turns out the first one listed is the one that gets used. So in effect, even though I have multiple default gateways defined, only one is actually used, and it's the topmost one in my routing table, which is this one. So here's my problem. When I'm putting together packets to send outside of our network, they're being sent to a machine called 192.168.10.1. And that machine doesn't exist. Or maybe it's not routing things properly. But for whatever reason, traffic is not passing through that IP address or the machine connected to that IP address. So here's what I'm going to do. I'm going to do a route del to delete that route from my routing table. So now I've gone back to only having one default route. And now all of a sudden, things start working the way I expect. And if we do things with DNS names, everything is operating the way I would expect. Because now, thanks to my routing table, um, if I'm sending traffic to one of my two directly connected networks, we just put it on the interface and it goes on its merry way. But for anything else that's not addressed to one of my locally connected networks, it goes to this machine 10.0.2.2, who receives it and then figures out how to pass it down the line. So the problem was that I had a bogus or non-functioning gateway in my configuration, and it was listed first, which meant that that was the default route that my machine always passed traffic to, which is why as soon as it got there, it just kind of died because it wasn't being passed to the next hop in the chain. All right, so how does this happen? Well, in my case, I actually manually added the bogus route, and that's why it was added in there. But I've also seen this happen when you have multiple network interfaces configured on a machine. One of the properties that we set with network interfaces is the gateway that goes along with it. And so if I take a look at nmcli connection show emp0s3, and I look for gateways, I don't see any configured, except down here, it was a part of my DHCP lease. So that's how I got that correctly functioning route. But what if I had two network cards and each of them was provided a default gateway as part of its DHCP lease? Or each of them had a configured gateway as part of their statically defined settings? Well, in that case, whichever one is activated second would actually be the preferred route. And so you start to get into some weird stuff when you have multiple gateways defined for each of your connected interfaces, where whichever one is activated last becomes the default route. And if that route is not working properly or is incorrectly defined, all of a sudden traffic gets weird. The other thing is realized that when we started to route traffic with that other address, it actually started routing through a different interface, which could be connected to a different VLAN in our local network and could have different rules assigned to it. So, making sure that you have one default gateway defined in your configuration is going to make your life much easier. With things like DHCP, you'd always have control over that. But if you're defining your secondary interfaces with static networking, defining the gateway is one of those settings that you can define in your static networking. So I would recommend having one default gateway for the machine, not more than one. And if you do have more than one, realize that whichever one is at the top of that routing table, that's your actual default gateway, regardless of how many others are defined. Now, there are some crazy difficult network settings that you can put into place that will have a bunch of routing rules where you can utilize more than one, but that's pretty uncommon to see. And in fact, what I just showed you is the more common problem, which is you have more than one default gateway and the wrong one gets used by accident. So that's how to troubleshoot routing problems. All right, we are approaching the end of our time together, but I wanted to talk about one last thing before we're finished. Um, Earlier, we're talking about the different tools that we have at our disposal. For each tool, I said, this is the protocol it uses, right? Pings use ICMP traffic, tracepath, UDP traffic, traceroute, ICMP or TCP traffic. And that is important because it turns out um, administrators can set things on their machine that will cause them to behave differently. So give me just 1 second, producer Eric, and I'm going to mangle this machine in a different way. All right. So if we bring up the machine, um, if someone were to try to ping this machine now, it wouldn't work. Oops, sorry, wrong one. Ping 127.0.0.1. Somebody tries to ping its IPv4 addresses, it won't work. Because it's the administrator, I have turned off ICMP protocol echoes. So my machine will receive an ICMP packet, and instead of sending an echo response, which is the normal behavior, I'm throwing that packet away. And that's going to affect things like trace routes as well, because a trace route will by default send ICMP traffic, and this machine, when it receives ICMP traffic, throws it away. So we can see that this machine has a like 100% packet loss, but its networking is working fine, right? We can connect to services running on this machine fine. So if somebody were trying to connect to this machine via the web service, it would happily provide web pages. Or in our case here, you can see it's happily providing SSH services to an SSH connection. But if someone were to ping it to see if it was alive, nope, would not respond. And whoever is actually trying to ping it might assume that the machine is non-functional. All right. So the actual setting that changed is a kernel setting. So this setting is defined in the Linux kernel, and I flipped this to a 1, meaning I am now ignoring all ICMP echo requests. So I receive an ICMP packet. Normally, I would send an echo to say, yes, I've received your packet, but now not responding at all. The default for this configure for this file is 0, meaning you will respond to ICMP traffic. Um, the reason it worked when I just typed in the word localhost is because there's also one of these for IPv6 interfaces, and I didn't manipulate that one. So when I did a ping localhost, notice it was responding back from its IPv6 address, colon, colon, 1. So that one is weird. So if you're manipulating this, you need to remember to do it in both places. Um, but that's why it's important to know what type of protocol your diagnostic tools use, because maybe ping's not working, so I should use tracepath, which uses UDP traffic. Or maybe I should use tracepath with a port number to see if I can connect to a service running on that port number, rather than relying on something like ICMP echoes, which we know the administrator can turn off. Or maybe I want to use traceroute and connect to a TCP service because not every machine will allow UDP connections, right? Like um, web services by default don't do UDP connections, but they will do TCP connections. So knowing the protocols, the actual like network protocol that your service uses or that your machine uses or your network diagnostic tool uses are important because that can help shape your data to know what the real disposition of what's happening on the machine is. Um, so that was my last word of warning of is know ICMP, UDP, and TCP and what those mean and the tools that use them. All right. So I see that Fernando very rightly saw that I had configured my machine to discard ICMP echoes. That's actually a really common thing, and you'll notice early in the segment, I was using tracepath and we're getting no replies. That's what's happening there. We're getting no reply from the machine that got that expired packet because there's been a configuration to not respond to the expired packets. All right. So don't forget to try out one of our labs at lab.redhat.com if you're interested in learning more about Linux and Red Hat Enterprise Linux. Next week, we're going to be covering boot problems. So again, we'll do some whiteboarding. We'll have a tool set. And next week, I'll have our friendly neighborhood Nate with me as well. So he will be returning next week for our next episode. We're also going to be having a RHEL Presents next week with Yubico, talking about how we use YubiKeys as multi-factor authentication with Red Hat Enterprise Linux. So see you next week. Enjoy RHEL Presents on Wednesday next week with Yubico, and I'll see you in the ether.